Previously in this course, we've really relied on the molecular formula to determine what a structure is. But because we use so few different types of atoms, namely carbon, oxygen, nitrogen, and hydrogen, with some other ones that are similar to carbon, oxygen, and nitrogen, we really need to know how the atoms are connected in order to define the structure. It's simply not enough to know that there are 2 carbons, 2 oxygens, and 4 hydrogens. That is not enough information to describe what this molecule looks like. So we want to look at a few different representations of structure. And the first is one that we've already known, and this is all going to refer to acetic acid. This is the acid in vinegar that is shown here on the right. C2H4O2, this is called the molecular formula, and this is still true, right? This is acetic acid's molecular formula. However, it doesn't tell us enough information about this molecule. It's ambiguous. We could connect 2 carbons, 4 hydrogens, and 2 oxygens in ways other than this way that's shown here. And so the pro of molecular formula is it's compact, it's explicit, it's great for beginners. This is still a formula for acetic acid. And the con, and it's a big one, is it doesn't tell you anything about how the atoms are connected. And so this is a real missing piece in the molecular formula that we really want to address when we are considering other representations for acetic acid. And the first way we can do this is with this condensed formula. And so now instead of writing C2H4O2, I'm going to say this is CH3COOH. And before we go on, let's look at this acetic acid molecule and read the molecule from left to right. I see at first a carbon with 3 hydrogens, right? That's that first carbon that we're looking at. I'll call that CH3, and that's why CH3 comes first in the condensed formula. Then we have this carbon double bonded to oxygen, bonded to an O with an H group. It looks a little complicated, but this is a really important group to recognize in organic chemistry. We call this COOH, right? Because as we read it left to right, that's sort of what's there at the end. And so when we look at acetic acid, this kind of breaks down the different pieces of the molecule. There's CH3 bonded to COOH. And that's how we write this condensed formula. And if we look at this condensed formula, we can see that this does really show the structure explicitly, remembering again to follow all the rules that atoms like to have. Carbon likes 4 bonds, oxygen likes 2 bonds, 2 lone pairs, and hydrogen just sort of caps things off. And so this implies information about bonding, and I think does so pretty unambiguously. In this case, unambiguously, more complicated molecules, it can be harder. But the challenge is that it's still tough to see the structure, and it can feel a little less accessible to beginners compared to the molecular formula. However, if we're just needing to write a formula that describes a structure on a single line, this will do the trick. But the gold standard for organic chemistry is called the skeletal structure, and it looks something like this. The Lewis structure is great, and that is important to know is what's represented here. But organic molecules get a little bit large, and drawing out every atom, every lone pair can be a bit arduous. And so this is the skeletal structure for acetic acid. And the pro is that it shows the entire structure, and we're going to get into why this is on the next slide. But the con is that it's no longer text, it's effectively an image. This is an equivalent representation as our Lewis structure, which is shown here for acetic acid, and it also does take just a little know-how in order to interpret. So again, these are equivalent, right? These are equal representations of these 2 structures. And why is that? Well, first of all, when we look at the skeletal structure on the right, everywhere that the lines end, like all of the ends of a line or the little vertexes, right, the corners, these are where no atom is specified, but an atom exists. It's carbon. If it's carbon, we don't need to show that it's carbon. And so as we kind of detail these rules of the structural formula, take a look at the Lewis structure on the left and the skeletal structure on the right, and just note that they are the same, right? At the end is carbon 1, and at this junction between the oxygens is carbon 2. No atom specified means carbon. Here we have hydrogens, right? In the middle one, all the bonds are satisfied. We can see that for the middle carbon, there's 1 bond going to the left and down, 2 bonds going up to the oxygen, and 1 going to the OH oxygen. That's 4 bonds. But when we look at the skeletal structure and see the terminal, we see that it's only bonded to one thing, but carbon wants 4 bonds. When we see this skeletal structure, if it doesn't have enough bonds, we know that hydrogen is filling the remainder because, again, carbon always wants 4. So very explicitly as part of the skeletal structure, we know that there are 3 hydrogens that are at the end carbon here, even though they're not shown. We don't need to show them because this is just how chemistry works for carbon in 99.9% of cases. In those rare cases, which we're not going to cover in this course, we can denote that some other way, but the default is that hydrogen exists there. And finally, when atoms have lone pairs like oxygen, we learn that oxygen likes to have 2 bonds, 2 lone pairs. They're assumed to be there. We don't need to show them. Again, if there's some sort of an exception, we could show that, but that's a bit outside the scope of this course. And when we look at this skeletal structure, there are 2 lone pairs implied on each of those oxygens. And so with these rules in mind, I hope you're able to see that the Lewis structure on the left, which is a lot more writing, is exactly equivalent to the structural diagram on the right. Lewis structure on the left is equal to the structural diagram on the right. And furthermore, the structural diagram on the right is drawn in a way that reflects the actual geometry of this molecule, making sure that there are angles and not kind of laid out like plus signs, is just something you'll get used to viewing and is an important part of interpreting these structural formulas. So if we look at the following, right, let's look at this molecule here. Take a minute to look at these and determine which one is equivalent to the one shown below. Go ahead and pause, and then I will show you which one it is. All right, which of these do we think it is? It's going to be this middle one, right? This is called ethanol, 2 carbons that has that prefix eth, and we haven't really gone over this, but when we have an OH, we end with an ol. So ethol, but we call it ethanol. And this is a molecule that maybe you've heard of before. The main point here, though, is when we look at this Lewis structure, we see there's 2 carbons, so we need the end of the line, and then we need a corner, and then reaches out to the OH, and this is all you need. It's much shorter than drawing the full ethanol Lewis structure, and it describes it completely. Here on the right highlighted is the skeletal structure of ethanol. Okay, now draw one for your own, right? Let's look at this molecule, and go ahead and pause here and try to draw it out, and then I will show you my answer too. All right, hopefully you've been able to take a stab at this. Here is the structure, the skeletal structure for this. We want to make sure there's 3 carbons. That's very important. So carbon 1 at the end, then 2 is corner 1, 3 is the next corner, and then the OH at the end. We do need to show the oxygen as part of this molecule. And this is going to be propanol. So this is a OH, so it's all. Prop is 3 carbons. And again, that's just kind of to reflect what we've looked at in previous slides. But what's most important is that when we see this structural formula, we see this molecule. 3 carbons, saturated, meaning filled with hydrogens, and we have an OH, no double bonds. All right, we've looked at that one. Now let's do a condensed formula to describe the molecule below. Again, this is where we are trying to get it into a single line and show what exactly the molecule represents. So go ahead, pause here, and then give the condensed structural formula a try. All right, this I would call CH3, CH2, CH2, OH. And this looks a little redundant, but again, reading the molecule from left to right, I see a CH3 that's at the end where we have 3 carbons. Then there's a CH2 that's kind of like a linker, then another CH2, linker number 2, and then the OH. And if we read CH3, CH2, CH2, OH, we can only get to this molecule. That's what that's showing. We might also write it like this, right? This is a CH3, then 2 CH2s, then the OH. Here's another way to represent it. It's not that useful here, but this is a way you might see the condensed structural formula represented if this was much longer with, for example, 10 CH2 little linkers in the middle.